are on part 5. Path integration part 5. Can you believe it? Today we are going to see interacting theory with our first ever introduction to some pretty, how do I say
My
this?
My friend says you are a big pile of steaming something.
I can't be in the YouTube video. That's too good. Path integration part 5. Oh man. Very glad to have you here. Today, interacting theory. The subnetwork. Welcome. Hi there. Where am I? We're in a physics channel. We're gonna learn about physics. We're gonna learn about path integration. Let's talk about last time. It's been a week and a couple days since we talked about it. Last time, we had a couple things that we laid out, right? Like the functional derivative, the path integral or functional integral. So let's kind of write that up here because we're gonna need it for a little bit, but this was the old functional integral. And it's gonna be z of j, which is defined as the inner product of the ground state on the ground state with some sources j, okay? And that had a definition. That was equal to the integral over all paths of the field times e to the I integral d4x. Hold on, let me get rid of this stuff up here. I have stuff from last night when I started my teaching for the semester. And then the Lagrangian 0 plus j psi. We're right on top of Bowser. Okay, we're gonna go with it though. Tensor product soon. Yeah, I'd love to do that. I'd love to do tensor stuff on starting Friday. I think that'd be a good thing. If I add more time to this stream, which I plan to and want to, I want it to be helpful to you guys, but I also want it to be helpful to my degree program, and I think tensors would be very helpful if I taught them. And then into general relativity, which I also need to work on, so. All right, so last time we talked about the functional integral, and we could simplify that. I don't know why I wrote last time there, and then I'm writing all this stuff up here because I want to keep it, because we're going to need it for a little bit. And we simplified this to z sub naught of j is going to equal, because remember we had the, we talked about how the sources are what's doing all of the work that's going to take it from where this is not 1, right, where it's some probability of happening a certain way. You needed the sources, or else you're just going from ground state to ground state, and the state is not changing at all along the way. Oh, I did not give myself enough room. Sorry, let me redo. This one's definitely gonna need more room. Is equal to e to the, let's do exp. I over 2 times the integral of d4x prime of j of x with our delta x minus x prime and j of x prime. Freaky diffraction interfraction patterns coming from the shirt. I know, isn't that funny? I saw that the other day and I thought that was kind of crazy. I liked it. Hopefully it doesn't throw you guys off. Maybe it's gonna hypnotize you guys and you guys will fall asleep. And if you fall asleep, then it won't be because of my talking. It will be because of the shirt. That's for sure. So let's consider now. So this is what we did last time, right? We did these two things. And from here we were able to define what the what the time ordering function is going to be for a free field, and then eventually get the amplitude of going from a ground state to a ground state. And we talked about all the different possibilities of those. And you can just press the up arrow to get to your previous input. Oh, that's cool. That's pretty cool. Let's do, so let's keep going. So let's consider, now we're into interacting theory. So this week we have interacting theory. And what does the interacting Lagrangian look like? Well, it's kind of messy, but we're gonna need it. So let's write it all out. The Lagrangian is equal to -1/2, and I'm gonna write it all out because we need to split it up a little bit. We'll have to split it into different parts. We'll take a look at all these individual parts and kind of see where they come from, see where they go, see where they come from. Someone finish that while I write this down. Now, if you've seen interacting theory a lot, then you kind of recognize a lot of this stuff. But if you have never seen interacting theory, then this whole Lagrangian is going to look weird. Auto music. It's it's all good auto music. It's all fun. It's all fun and games. I get it. We love Tyrion. Or speak. So now we have this interacting Lagrangian where we had some things that look familiar. Like without this z's here, this was our free field from last time. But now we have these z's that we're gonna like sort of, they're gonna come back when we need to do renormalization and stuff. So for now we're gonna like show how they progress through this, and then eventually we're just gonna drop them off until we need to bring them back. But this particular theory is called Phi Cubed. This is a toy model, and the Hamiltonian, if you have the notes are on Discord, so if you would like to follow along with me as I do this, I publish the notes, or I don't know, publish is the wrong word. I post the notes into the Discord channel labeled Path Integration. Notes even, maybe? I don't know. Path Integration something. And you can go check that out. I have the Hamiltonian there, and as you can see, the Hamiltonian has some negative terms that are different than these. And the negative terms exist on these, and that means that we have negative energies, infinitely negative energy states. If you have paid attention to, if you've taken quantum mechanics, you know that like cubics as harmonic oscillators don't work well. And why? Because the particles have the ability to tunnel and then just ride the end of the cubic wave down. Because you know it's going to want to go to the lowest part of the potential, which is not good if we have a cubic. So that is all in Shrednicki if you would like. Shrednicki we are following, if you're new to this, we are following Shrednicki, and he has a PDF of this book on his website. But there is, he does make note that it's a draft and there's a couple minor errors in it. But the book, I looked at the book several times on his website and it's good, it's very good, and it's free, so I don't know. It's really good. It's amazing that he would do that. So I'm not too worried about the normalization stuff in the notes. If you want to see the normalization stuff that I put in the notes or want to talk about it, that's fine. But most of that stuff is sort of just to put bounds on how this wave function is going to behave, or how these fields are going to behave. And we want to keep certain normalizations, like what is the momentum going to do?
The link to the book is on Discord.
Awesome, Tyrion. Thank you. And there's all sorts of interesting things you can, or not interesting things, but we want to make sure that the normalization is the same. Especially like if we were to dot product the two, you know, the two zeros, the two ground states, and set j equal to 0, that's got to be equal to 1. And there's things like that that normalization need to have. They're all in the notes if you're curious about that, but I'm not going to go too in-depth into that right now. How does a particle gain a wave function? What are the criteria? So every particle has a wave function that describes it. That is something that's really complicated to describe. If you want to know more about the fields themselves, you can, I have a YouTube video that describes it. I think it's like Introduction to Quantum Field Theory or something along the lines, where I kind of like introduce the fields as wave functions and you can sort of see how they look like. In a space we call Fock space, which is basically like a space where you either have a particle or you don't. So that's all very much explained in that YouTube video. I think it's Introduction to Particle Physics or Introduction to Field Theory or something like that. And that's the video you would want to see, like how it kind of looks, like how this kind of takes place, if you're curious about seeing that. But for the most part, we talk in quantum field theory that particles are just excited states of fields. So you have a field that behaves like a wave function. It's like a field, you know, and it has a wave function. And then you can excite it and you get a particle. And that's how quantum field theory is done. So that's what we're doing with this. So we have this interaction Lagrangian. We don't really care too much about the whole thing. We'll have some time defining these a little bit. And these are going to end up coming back later in later lectures when we're talking about renormalization. But for now, we don't really, we'll kind of define them in a second. But this is the Lagrangian for an interacting theory. It is a Phi Cubed theory. See, this is Phi Cubed. It dictates the interaction term, which is this one. And that is the interaction term that we're going to be highlighting today a lot. So let's talk about the goal for this chapter, which is going to be a span of 2 days, today and probably next Wednesday. The goal is going to be to evaluate the following integral. Today's lesson is not very long, by the way. We've already started, but it's also like, I only have a few pages of notes because this stuff is going to be fun. We're going to look at Feynman diagrams and kind of like what they mean and what they do and stuff. So here's the goal, is to evaluate the following integral. If we have some z of j, so this is a new functional integral, and what does this new functional integral look like? Well, it looks like the following. We have a ground state dotted with the ground state. So we're looking for the amplitude that some particle is going to go from a ground state to a ground state, but something's going to happen in the middle. Ash. You'll see, if soon it's just going to turn into fun diagrams, that it's all about particles, and that'll be fun. So this integral is going to be the integral over all paths from the ground state to the ground state times the exponent to the I. And then this is going to be our action, but our action is going to look a little different. Why? Well, because we're going to have another term, obviously. We're going to have the term of the interaction term, right? So now we have an interaction term, Lagrangian. If you guys remember, I think this is going to be from week number 2. From part 2 of our path integration series, which is, if you want to do the whole thing, if you're interested in learning path integration, you can find it on my YouTube channel, as well as some other fun videos, especially one where Professor Melko is the highlight of the video, the meme review one. He's the star. But we did this, I think it was week 2, where we kind of like laid this out as an interaction Lagrangian term, right? So we have what we did last week, where we see our base Lagrangian and then our source. And now we have the base Lagrangian and the source plus this interaction term right there. We can then recast this integral. So this is what the goal. We have to evaluate this integral. We can recast this integral the same way we did in week 2, where we set this equal to some exponent of I integral d4x times the Lagrangian of 1 over I functional of j of x all multiplied by the rest of the integral, which is the integral over all paths, e to the I integral d4x times the rest of the Lagrangian. Now, the rest of the Lagrangian being this term without the interaction. If you remember from week 2, this was what we were able to do, is use this to, is there supposed to be a 1 there? Yeah, there is, for the interaction term. This is what we used to redefine the interaction term of this Lagrangian. We could say, hey, you can make whatever interaction term you want by taking functional derivatives of this guy. And that's the goal. Organic with Grace, welcome. It's like topology, man. It adds wavy lines to it. I think it's awesome. Hopefully it's not bothersome. I hope it's fun. And then what we can say is, well, this is going to be some sort of proportionality to it. Why is it proportional? Well, it's necessary for normalization reasons. Again, a lot of this stuff, if you were to actually want to do a lot of calculations with it, you would want to have everything normalized properly. So most of that stuff is in the notes, the beginning of the notes. If you're not part of my Discord, !Discord, and you can go and pop in there and you get the notes yourself. So again, this is just like we saw last time, right? We have this here, we saw this. This is the free field, and we know how to rewrite that. We can rewrite this. We can recast it as just this, where we say, okay, we're going to throw away all of the normalization stuff that takes the ground state to the ground state. We know that if a particle starts in the ground state and it ends in the ground state, there's one configuration where it just goes from ground state to ground state and nothing fun happens. It's just boring. So yeah, if you go from ground state to ground state, there is one possible way of going from there to there without anything happening. So we're going to kind of divide that away. We get rid of that, and then what we get this guy right here. So let's go ahead. So now this becomes this. That's what we did last week. And then we're going to place this under here. So we really have, this is proportional to e to the I lambda d4x times this interaction Lagrangian 1 over I functional derivative of j of x, all multiplied by this, which is the exponential. So it's two types of e's. I'm writing the exponential of I over 2 integral of d4x prime, j of x, and delta x minus x prime, and j of x prime. But so we have these two exponentials, and we know that this is a functional derivative of j of x. So if you remember your derivatives from calculus, you have the derivative of something, of some variable. And functional derivatives just mean the derivative with respect to some function. So now we have a derivative with respect to some function. We have those functions exist here. And we can go ahead and, if these were not in exponentials, we could carry out this functional derivative how many ever times we needed to, right? So how do we get it out of exponentials? Well, before we get into that, let's talk about what this, what we get for our base Lagrangian and our Lagrangian interaction. So let me erase some of this stuff. One day we'll understand. Awesome. Thank you for the follow, Jayu. Appreciate that. Welcome, everybody. All right. So let's leave these up for another second longer. Actually, let's erase them. We don't need them. We can keep going. Now, let's talk about that Lagrangian. This, I guess we did need that. Well, it doesn't really matter. We can talk about the Lagrangian as it is. What did that Lagrangian mean? Remember that Lagrangian was ultimately from last week, the base Lagrangian, and that we defined as -1/2, and this was the Lagrangian for the free field, the free propagating field, and -1/2 m squared, phi squared, and we had in our big Lagrangian, we had something that looks like that, but we also had our interaction Lagrangian. So we have our interaction Lagrangian, we had our actual Lagrangian for Phi Cubed theory, and then we have this base Lagrangian. And we know that our full Lagrangian, this guy, has to be equal to our base Lagrangian plus our interaction Lagrangian. So if that's the case, if this is our base Lagrangian that we know, we've decided last week that this is going to be our base Lagrangian, then we only add the interaction Lagrangian. How do we get from this base to this full Lagrangian? Well, our interaction Lagrangian is going to take take this shape, right? And this is where it's going to get a little bit, I don't know why I keep putting I there. It's not I. So our interaction Lagrangian, we can say it looks like this. 1 over 6 ZGG Phi cubed plus, and the reason I say this one is because remember I said this one was our interaction term. If you are familiar with the interaction term, you know that this is the coupling constant. Ethereal, welcome to the channel. Did I say that right? And where is it? I've lost my space. Okay, so then we have this other thing that we'll call counter terms. Now remember I said that those z's are going to come into, awesome, great. Those z's are going to come into come into play when we worry about the renormalization, but let's just sort of see what this is. If we want to get back to our original Lagrangian, we have to know what's inside here, so let's write what's inside this counter term Lagrangian. That's going to consist of the -1/2. We're going to bring back the z of phi minus 1 because this 1 is coming from here, and that will come into play in just a moment. That one doesn't exist in, this one doesn't exist in this Lagrangian, so we have to make sure we get rid of it somehow. So we'll be getting rid of it by adding another term to the counter term Lagrangian. Phi, what else we got? Minus 1/2 Zm minus 1 m squared phi squared plus y phi. Now, if we add these things to the Lagrangian, then what happens? Well, if we add these two Lagrangians, or I'm sorry, if we take this and plug it here, and then we add these two Lagrangians, then we ultimately make it back to our main Lagrangian that describes Phi cubed theory. Now, what does this mean? Well, we always have to go back to the case where if we have j equal to 0, we want to go from 0 state to 0 state and have the normalization to be to 1. What that means is in order to get to that thing, we also have to say that this can be a non-interacting thing. If this is non-interacting, then we want to be able to just have our non-interacting Lagrangian. What do we need? Well, if we want, so what do we choose? I guess I'll answer it right now since there's a question about like this. How do we know it's interacting? Well, we've already done the non-interacting field theory. We've done a free field theory propagating, so now we need to have something, yeah, that's fine, NC, I got it. So we need to have something that's interacting, or we need to have something that's interacting because we already did the non-interacting case. So how do we talk about something that would be interacting? Because we know things do interact. So we need to have some way to handle it. So we have a phi theory that has a interaction, a Phi cubed theory that has an interaction term in it, and we've already established that it's not physical, it's a toy model, but we can still do some good physics with it. And then we can like extend that to some more physical structures. So if we want it to be non-interacting, we want this to go to 0. Well, what does that mean? Well, that means this stuff has to go to 0 too. So we can see that if g goes to 0, what has to happen to everything else? Well, then we need y to go to 0. And then we also need zi, so both of these z's have to go to 1. That way, everything will go to 0 with it, and it will be fine and dandy. But that's not always going to be the case. There can be some situation where, well, we're going to have a lot of situations where g is not going to 0, so therefore there's no reason for all this stuff to go to 0, and we'll have to worry about this stuff later. But for now, let's take this whole Lagrangian and put it on hold, and just put it off to the side. We won't bother with it, but we'll have to bring it back up again later. Let's just look at this interaction term right here, okay? So if we take that interaction term, we can define the following. Now we're going to have a new functional integral that's going to look like this. It's going to be proportional to the exponential of I over 6 z g times g times the integral of d for x times 1 over I functional d dj. And this is going to be cubed because it's a cubed field theory, right? Cubed phi. Basically what we're doing is getting this phi, this term right here, into our form of Lagrangian, right? Our functional integral, excuse me. And then this is going to be multiplied by our j sub 0, which again we've seen several times now today. It is an exponent. It's an exponent of the integral of j of x with the integral in the middle. CVS fan. Hi there. Welcome. Okay, so what have I done? Where are we at now? Oh yeah, so now we have both of these things in our exponential. We've gotten our Lagrangian interaction into some functional integral, and now we have to get out of the exponent so that we can actually start taking this phi cubed, this Lagrangian, wait, did I? Oh yeah, that's right. This Lagrangian, this phi cubed, into our z sub 0, okay? And we're gonna need to do a little trick. We're gonna need a little trick for this, okay? It's gonna be 2 Taylor expansions, you know, as you would Taylor expand an exponential. That's something that we all got to do when we take physics is Taylor expand exponentials, but we're going to kind of establish certain things for it as we get closer and closer to defining a Feynman diagram. So let's write this monster out, and this is going to be the thing that we use to define where the pieces of the Feynman diagram come from. So we're going to have two Taylor expanded exponentials, and we're going to expand the first one with a v. Yes, there's a very specific reason that we do v. Is this song on repeat? No, I don't think so. 6. And then the integral of d for x 1 over I functional derivative with respect to jx, where this is cubed, and this whole thing is brought to the v, and this is times Black Rose, thank you for the follow, welcome. The sum of p, and we're gonna do this exponential in terms of p, for a very specific reason why we chose v and p. And this is, what do I have here? Oh, I over 2, integral of d for y, d for z, j of y, with our propagator in the middle. Yes, that's right. Our propagator in the middle. jz, oops, that's not a z, that's an jz. And this is all going to be raised to the power of p. That's how we do these exponentials, these Taylor expansions. We can carry out every single term in this Taylor expansion, right? So think of all of the possible v's and p's you can do together. Obviously, we're going to have a 0, 0, and then we'll have a 0, 1, and we'll have a 0, 2, and we'll 0, 3, etc., all the way to infinity. And then we can go up to v equals 1, and then we'll have 1 times 0, 1 times 1, 1 times 2. We can do all of these different expansions. This whole sum times this whole sum, wholesome, how wholesome, is going to be what we get for this one expansion. Now, how does that help us? Well, we just have like some infinity series times some infinity series, and that's supposed to tell us something about, particle interaction. Whoa, it's like Inception. You know my shirt? Should I like dance or something with the shirt and the bard? I don't know. Feels weird. Okay. But what we can say, if you remember what this is from the few weeks ago, this is always going to get us the amplitude of a certain interaction. So how do we go ahead and solve this? Well, this is actually technically all of the interactions, right? Because it's over all paths, where each individual path from the ground state to the ground state is one path, or is one probability. Each of them has a probability of happening, right? And each time we take one piece of this and multiply it by one piece of this, then we get one path. So when you hear about the path integral, right? And this is what most people get very confused about when they hear the path integral. They don't understand. They're like, oh, you sum over all paths, so how does a particle take every single path at one time? How does it do it? I don't know. It doesn't take a path. One particle does not take every path at the same time. There is nowhere in physics do we actually believe that a particle physically travels every possible path at one time. Well, there's some people that believe that, but most of us don't. Well, there's a reason I chose the V and the P, or I should say Shrednicki chose the V and the P. It's clever. Stick with him. People have requested path integration is one way to put it. They did, it's just they stopped coming. Except Tyrion. Tyrion asked and he's still here. And Admiral still comes, so it's not very fair. But yeah, it's funny to me. But we're still doing it, and it's good. It's healthy for me, and I like teaching it, so. So never on the path integration, when we go, do physicists believe that a particle will physically travel every path at the same time? Instead, what we do say is that for each path, oh, Rooster's still here too, definitely. what we say is each path has some probability associated with it, right? It's a superposition of every single path. Like, well, whatever works, I guess. Awesome mind. Yeah, so what we're really saying is each individual path has some sort of probability associated with it. And when we move into Fock space and we start talking about going from the ground state to the ground state, we say a path is like how something can travel in Fock space. Basically, can you go from ground state to ground state, and all the different ways to go from one state to another. Does it go up to one particle down to the ground state? Does it go up to two particles and down to the ground state? Does it go from particle to particle to particle to particle to particle to particle to particle back down to the ground state? Like, we don't, like, this is all of the different paths that something could follow, and we have to include all of them. Electron orbitals, yeah, you could definitely do path integration to talk about electron orbitals, and then you could say, like, which path is the electron taking when it orbits? You can definitely integrate over those paths. And I don't know exactly what that would look like, but that's crazy. Okay, so let's get to these things. So now that we know that we're talking about all the paths, and we can actually see a probability scheme forming, every single one of these combinations can somehow get us to a probability of this specific thing happening. So what do these mean? Well, like I said, we chose V and P very particularly. We can now establish some E, which is equal to 2P minus 3V. Okay? So let's say, like I said, so all V from 0 to infinity exist, all P from 0 to infinity exist, and we're going to multiply them together. But now we're also going to have some E that is equal to whichever value of P and V we are at. So we'll have 0, 0, 0, 1, all of those possibilities will exist, and E is going to be given by this combination. What do these mean? E is what we call an external line. It means this is how many vertices you are going to, or I'm sorry, external lines. This is how many sources you are going to end up with after you subtract, 3 times V from 2 times P. What do those mean? Well, P is going to stand for propagator, and yes, that is the same propagator that we have been studying. That is the Feynman propagator even, if you would. And V is going to be given by the vertex. These are the necessary components for making a Feynman diagram. The propagators, the external lines, or the sources, external sources we'll say, and then the propagator, the vertex, and the sources. Now, as you may have probably guessed, diagrams can be constructed in the same way, and we'll end up overcounting some diagrams. So, like, you can definitely get combinations of this that are going to repeat itself. But we'll have a way to handle that we'll talk about next week when we talk about symmetry factors, because that's what that is. But this is our foundational parts of the Feynman diagrams. What do these look like? So for these diagrams, the external source is going to be a solid dot with a line. That's basically your field. And then external field. And then you'll have a propagator, which will be in between fields. And that will just be given by a straight line. And that will be in between vertices, excuse me. It's in between vertices. And what does a vertice look like? Well, it's going to be like, you'll have your 3. You can have, for Phi cubed, you're always going to have 3. Notice that there's always going to be a 3 associated with this. These are multiples of 3, so every 3 will have some vertice or whatnot. And then that's always going to be some connection point between 3 fields, or 3 vertical lines. 3 sources. Now, what does that mean? Well, if you were to have a different field, let's just do one. What's one that we basically think of? Well, how about if we just have, 2 fields come in, they meet at a vertex, and then 1 comes out, right? This might be what you would see if you were to look at a certain, this is what we call a tree level diagram. There's no loops in it. It's just external forces with one vertex. And you can actually write down everything that's associated with this. How? Well, we know the propagator, right? The propagator is given by, let's establish some Feynman rules. I don't know where to write them. I guess I'll write them on this side. But we need Feynman rules, right, to carry out calculations. So for our external forces, each one is going to be represented by a d4xjx. Our propagators are always going to be given by the 1 over I, and this is going to be the delta x minus y, something that we did last week. I think we did x minus x prime, same concept. And then the vertex is going to be I, z, g, g, which is the coupling constant again, d4x. Now, how does this work? I don't think I ever answered that. How does this work where we can have infinite amount of terms and get reasonable probabilities? Well, this g is very tiny. We called it, oh, you can't see it because the camera's in the way. Let me move this out of the way. Oh yeah, you can see it. What? Okay, this g is very tiny. So once we get to higher orders of v, this is like taking a very tiny number and squaring it, which is even a smaller number. How about cubed? Well, now we have g cubed, which is even smaller. So eventually there's going to be levels of v, and it's pretty quickly. We don't go very high with this, till we get to the point where v is like 3 or 4, and g makes this entire thing next to 0. And that's how we get away with using all of these infinite terms. We only have to go up to a certain level to make sure that the perturbation doesn't affect the probabilities anymore. So there's going to be the probabilities where the higher the v, the less likely it is to happen. That's what we're talking about, the outskirts of these paths on the path integration, the ones that are less likely to travel. So we have this, and every time we make a diagram, we can use our rules that we've defined here to figure out a quick calculation of how to describe it. So let's see some Feynman diagrams. These are directly from Shrednicki. So we can take a look at these Feynman diagrams. This is from the text that's available online. And let me see here. Split. Let me find this. Okay, so if we look at these Feynman diagrams, there they are. This is the funny part about that meme that Justin sent me. So Justin sent the meme into the meme review, video available on YouTube, and it was, we're not talking about this or this, we're talking about this, the SpongeBob thing. And he starts with the meme. I don't know if anybody can find me the SpongeBob meme really quickly that I laughed very hard at. But he starts with the tree level diagrams. And the tree level diagrams are the easy ones. That's like this, or better yet, this, right? So here we have the same one that we have right, there, right? A nice, easy thing. We have one vertex. We have 3 external lines. So we can go ahead and go to our rules and construct an integral that exists with one vertex, so we'll have one of these, and 3 external lines, so we'll have 3 different sources, right, that go into it. And each of these evaluated as just some field. This looks a little more daunting. The external sources look a little more daunting than they are. Don't get too worried about those. You can find a definition for that straight up in Shrednicki pretty easily. But these are the tree diagrams. This is another tree diagram right here. You have 2 in and 2 out, but notice that each vertex, one right here and one right here, has 3 fields going into it, right? That's the important part of a Phi Cubed theory, is there's 3 fields going into each vertex. And then, so this one and this one are relatively easily calculable. You can just sort of enter the rules in and you'll get some integral, and then you can calculate that integral using tools of some kind. But very soon, you can see that these become pretty chaotic. Now, all of these diagrams exist because every single possible version of diagram exists multiple times within those 2 exponentials that we have. These 2 things right here. Each Every possible combination of fields exists within that. And we can eventually get to, did I skip it? Did I skip it? Oh, I did. I have a fun little thing for you too. Every single one of those exists, and there's a formula that describes that. Spoiler alert, yes, I'm a doofus. Let me tell you how many ways you can write all of the diagrams down, right? And then somebody tell me what this is. If we have some combination of propagators and vertices, there's going to be the following combination. This many diagrams exist for this number of propagators and vertices. What is that called? It's a permutation, right? It's a permutation. Hi, ready? 409, how are you?
The answer is 5.
The answer's not 5. This is a permutation, right? We're permuting all of the possibilities. I mean, I guess. And see, it's like you always learn those two things, right? Combinations and permutations.